So again, this is a kind of a short summary. For example, we apply sinusoidal input to a linear system and generating sinusoidal responses at the output. Any system, but output is different in amplitudes and phase angle. Here, the difference in amplitude and phase angle is a function of frequencies. So the frequency means that is the frequency of the input signal. So now we need a proper mathematical and graphics analysis method. So that is why we are moving to this Bode plot. So here Bode plot is giving us two important terms, that is the magnitude and phase. Magnitude means what? Magnitude is nothing but output magnitude divided by input magnitude, maybe in terms of voltage, output voltage divided by input voltage, that is the transfer function. We have a math derivation such as output voltage VO divided by the input voltage VI, that's correct. It's called a transfer function or gain. A is equal to VO divided by VI. If you calculate, so this is just a transfer function. If you calculate magnitude of this transfer function with respect to frequency, then you will get magnitude frequency response. So what we are seeing in this slide is the complete summary of what we had seen. The important points you have to remember. So you have the transfer function, and then you are changing this transfer function in terms of magnitude with respect to frequency. That is why you are using the formula I mentioned here, this important formula. dB is equal to 20 times log of A with base 10. So this is the formula we are using to convert the transfer function in terms of magnitude in dB. So how to calculate the magnitude of this transfer function with respect to frequency? So you have to use logarithmic frequency scale. That is the formula you have to use. And after use the formula, you are plotting the graph. And then you will see how is the magnitude is falling down or it's rising. How is the phase angle? The phase angle is 0 degree or it's rising to 90 degree and then going down, going to flat again or something. So it's really up to us how we are performing the analysis by using the standard method. So far what we had seen is the standard formulas. And phase angle is the difference in phase change in the output signal phase with respect to input signal phase. So whatever the signal you are getting at the output, if it's same as the input phase or if it's different from the input signal phase. Sometimes we have the 90 degree or 180 degree or 360 degree phase difference. If you have 360 degree phase difference, it means output is same as the input. So the formula is like this: magnitude frequency response, m of omega is equal to mo of omega divided by mi of omega, output frequency response divided output magnitude divided by input magnitude with respect to frequency. And phase frequency response, pi of omega is equal to pi o of omega minus pi I of omega, that is the output phase minus input phase. So this is just the same thing. In many places you will see the symbol dB, that is decibel. It's the logarithmic measure of power gain. So the formula is 10 times log of, that is power output power divided by input power, and it's logarithmic. So because this we had already seen, 10 dB is 10 times change in power. If you use 20 dB, then that it means 100 times change in power. So 10 times another 10, so that is 100. And then if you have 3 dB, then it means 2 times change in power, so decade octave. And since power is proportional to V square, that is why For example, here just 10 dB, right? 20 dB represents 100. Why? Because power is always represented or proportional to this V square, voltage square. So that is why the 10 times 10, that is a 100. So a 10 times change in voltage is a 100 times change in power. Just remember, 10 times change in voltage is 100 times equal to 100 times change in power. So if there is only change 10 times, then but the output power will change in 100 times. So that is why we represent or we use this formula to calculate the magnitude. So 20 log of the transfer function with the base 10. 6 dB is 2 times change in voltage. So these are just the same thing. We write it in a different way. So on a logarithmic scale, the variable is multiplied by a given factor or for equal increments of length along the axis. That is why we use the decade change is log base 10, octave change is log base 2. So even though if you get confused here, but this is the overall thing you have to remember this part. So decade change is log base 10, octave change is log base 2. And okay, so I mentioned here the power is proportional to V square. So maybe you remember the formula for power. P is equal to V times I, right? Voltage and current. That is how we calculate the power. So power have more than one formulas to calculate. So the same power we can also represent by I square R, or we can also say this power calculation is V square divided by R. So you should remember this as a electronic or electrical engineering student. Power have several formulas. P equal to VI. What is Ohm's law? And the same P is equal to I square R. P is equal to V square divided by R. Now we are also considering the resistance in the conductor. V divided by R. So there are three formulas. So that is why we said like if the voltage V square, or this is the P, right? So if the voltage got changed 10 times, at the output power will get 100 times change. So let us say now, why I say that? Now voltage is just, if the voltage is just 1 volt, then 1 square, right, is equal to P. 1 square is just 1. But if the voltage got changed into 10 volt, then the power will be varied 100 times. So 10 square. So that is going to be 100 divided by whatever the R value. So you should know that if you remember these three formulas, that is very good. Okay, so one more formula for power. So I mentioned three formulas for the power calculation: VI, I square R, V square divided by R. We have one more formula that is called P is equal to E divided by T. So E is the electric energy. So in this formula, this is the power calculation. So E is equal to P times T, right? So the unit is watt hours. We know the unit of power is watt, and the time is in terms of hours. You know, in our home, we are using electricity, and they are calculating how much energy you are using, how long you are using with respect to time. So in the peak hours, if you use maximum power, then of course they will calculate the energy based on that. So how many watts per hour you are consuming, then they will calculate the money. So per unit, for example, now if this is 100 units, then they have a fixed price or they have a flexible price per unit, then they will calculate the electricity calculation. So most of us already have this kind of experience in our real life. So if you want to learn little more detail about these different kind of power calculations, you please go to this reference link I had given. So you also have the calculator to do these kind of calculations, but you should know what is behind Now we are studying about the frequency response. We are not really into these power calculations, but the power calculation is the very basic one. You should know that. So poles and zeros and transfer functions. A transfer function is defined as the ratio of the Laplace transform of the output to the input with all initial conditions equal to 0. Transfer functions are defined only for linear time invariant systems. This is the definition for transfer function. And the considerations, transfer functions can usually be expressed as the ratio of two polynomials in the complex variable plan, that is S. So that we had seen. And factorization. Factorization means a transfer function can be factored into the following form. So G of S is equal to K times S plus Z1, S plus Z2, S plus Zm. So this Z1, Z2, Z3 and so on. This is called zeros, and divided by S plus P1, S plus P2 and so on, S plus Pn. So this P is represented as a poles, or P means it's poles, zeros and poles. So the roots of the numerator polynomial is called zeros. This is called roots. Roots of numerator polynomial is called zeros. The roots of denominator polynomial, this is the denominator, is called poles. So you can see here I represented poles by P, zeros by Z. So you will not get confused. Z1, Z2, Z3 and so on. P1, P2, P3 and so on. So in any transfer function, we have zeros and poles. Based on these zeros and poles, we plot the graph. What I plot or Nyquist plot, whatever. So now one small problem, we will see that. Then it will help you to understand what we are talking about. You are given the following transfer function. Show the poles and zeros in the S plane. How can you plot these zeros and poles in the S plane? So S plus 8, S plus 14 divided by S times S plus 4, S plus 10. So here the 8 and 14, these are zeros. 4, 10, these are poles. Let's see here now. So what always how we say this, S plus 8 is equal to 0. Then it means S is equal to minus 8. This is a pure mathematics actually. These things I think you should already know these things. So S is equal to minus 8. Similarly, S is equal to minus 14. S is equal to minus 4. S is equal to minus 10. So we have to calculate all the S values. The upper part is called zeros. So zeros we can represent by 0. The poles we can represent it by X mark. So you know this is the graph. We have the y-axis and we have the x-axis. Now we are in the S plane. So now how many zeros I have? Minus 8, minus 14. So this is the minus 8 I represent by 0, and minus 14 I represented by 0. And how many poles I have? 4, minus 4, minus 10. So let me change color. So pole I represented by X, so minus 4 and then minus 10. This is a very simple representation of poles and zeros in this kind of S plane. So S plane means we have the real part and we have the imaginary part. So S is equal to pi plus j omega. This is the S plane representation. Remember, this is called S plane. So this is the real part. This is always represented in where x-axis, and this is called imaginary part j omega. So this is represented in y-axis. So of course, you know, here this is positive side and this is positive side, and this is negative side, this side, and this is negative side. So the graph have 4 parts. So this is how we are representing the zeros and poles in the graph. So this is the actual sheet of 5 cycle. You can see here 1, 2, 3, 4, 5 cycles, semi-log paper. I don't know these things. I think you studied in your Vidrago in the school how to plot this kind of graph paper, special graph paper. This is the type of paper usually used for preparing Bode plots. So the left side, this is called magnitude in dB, decibels, dB, and here the phase angle in degrees. So y-axis are different, x-axis is the same for both magnitude and phase. X-axis is the same, so that is omega. There is a 2 pi of radians per second. So you should know the unit magnitude in terms of dB, phase angle in terms of degrees, and here is the omega in terms of radians per second. So if you represent like this, so the gain term 20 log kb is just so many dB in this is a straight line on Bode paper, and it's independent of radian frequency or omega. So it will look like this. So this is the form, the actual function, and if you calculate the magnitude, it will look like this. You remember we have the constant, so minus 20 log of modular j omega is equal to minus 20 log of omega. This is just omega. When plotted on semi-log paper, it will look like this kind of straight line. And similarly, when we have the term 20 log j omega divided by z plus 1, then what we should do, we approximate it be a straight line of slope 0 dB per decade. This is let me change my color again. So it's just like a straight line. See here with a slope 0, but when omega is less than z, then what happens? Then we approximate it with 20 log of omega divided by z. So this 1 is gone. Then we have the term like this. And when omega is greater than z, then what will happen? Which is also a straight line on Bode paper with the slope of plus 20 dB per decade. Plus 20 dB per decade. So this is how you have to represent this Bode plot. And similarly, if you have the another term minus 20 log of j omega divided by p plus 1. Here you are talking about poles. Here we are talking about zeros. So how can we do this approximation? So if omega is less than p, then we use the approximation, that is minus 20 log j omega divided by p plus 1 is equal to 0 dB. That is the flat line. That is the flat line. And if omega is greater than p, this omega, if omega is greater than p, we use the approximation of minus 20 log of omega by p. Then it means there will be a minus 20 dB per decade falling. So you should know that the difference between here and here. So here omega is greater than zeros, then we have the positive rise plus 20 dB per decade. Here omega is greater than p, here greater than z, zeros, and here greater than poles. Then the same graph, but here is the opposite. It's falling down minus 20 dB per decade. But in the previous one, it's rising up. So this is really depending upon the omega value with respect to zeros and poles. And if it's less than poles and zeros, then it's going to be a flat line.